This is lecture 17 of Condensed Matter Physics 1. And we now start our discussion on how crystal structure is determined using X-ray diffraction. We have already learned in the previous 3 lectures what the crystal structure is and how many Brillouin lattices are there, and we want to determine, given a material, the crystal structure of this. So, this requires X-ray diffraction, and we are going to see how that gives you the structure. So, what we are covering now is X-ray diffraction, and a related concept is going to be reciprocal lattice. So, in today's lecture, let us start with how do we see diffraction of light from a grating. What happens in the case of light is, suppose there is this grating with small openings at distance d, and we have this light coming in. Far away, we have a screen, and this light gets diffracted, and you see spots at certain points. And the equation for these spots is very simple. The spots occur when the path difference is exactly equal to some integer multiple of lambda. So, if the angle between the incoming ray and the outgoing ray is 2 theta, then the angle out here shown by green is going to be theta, and you see that diffraction condition is 2d sin theta equals n lambda. So, this is pure optics. However, the condition you see is what you have learned in your BSc or previous classes. For X-ray diffraction, and you should not be surprised by seeing the same equation, because what we are really looking at is the constructive interference. And this interference is between waves coming from different slits. Now, X-rays you cannot see through ordinary slits. The reason is that the X-rays have a wavelength lambda of the order of angstrom. So, unless these slits are really within an angstrom distance of each other, you can't really see diffraction of X-rays through these ordinary gratings. However, in crystals, the difference between different scatterers, those are the atoms, is indeed of the level of angstrom, and you do see this diffraction pattern. But before we go there, let me first show you that actually what you see in diffraction is a Fourier transform. And Fourier transform of what? Let me explain that. So, in this diffraction grating, the spots you see are at angles when the angle between the grating plane and the X-rays is theta, or the deviation is 2 theta. Let us call this direction in the plane as z direction, and let me take Fourier transform of the grating. So, the openings are at z equals n d. So, I can write that the wave coming from each of this opening has some sort of an amplitude delta z minus n d, because it is coming right from that z, and take its Fourier transform. Of the grating opening, or whatever the scatterers are. So, I can also say I am taking Fourier transform of the scattering sources, because these openings are doing nothing but scattering the light. So, if I do that, it will be e raised to I k z delta z minus n d summed over n integration d z. I am summing over n because there are these gratings which are going from all over the place. So, I can sum from n equals 0 to, let us say, over n scatterers or n openings. So, this comes out to be equal to summation n equals 0 to n e raised to I k n d, where k is in the same direction as z. So, let me make that here. Here is k. This I can sum over e raised to I. If there are n gratings, it should be n minus 1, right. So, this n minus 1 for n gratings. So, it will be e raised to I k n d divided by 1 minus e raised to I k d, which I can write as e raised to plus I k n by 2 d I can take out. I am left inside with e raised to minus I k n by 2 d minus e raised to I k n by 2 d divided by, here I will take out e raised to I k by 2 d, inside I am left with e raised to minus I k d by 2 minus e raised to I k d by 2. So, the Fourier transform of the grating that I have made, let me make it again. This is the grating where the distance between the scatterers is d, and I am taking a pattern far away. I am taking this direction to be k and calculating the Fourier transform of the scatterer function. The scatterer function, if you like, can be given as f z equals summation n delta z minus n d, and the Fourier transform g k comes out to be e raised to I k n d by 2 e raised to minus I k n d by 2 minus e raised to I k n d by 2 divided by e raised to minus I k d by 2 e raised to minus I k d by 2, or this is plus minus e raised to I k d by 2, and this comes out to be e raised to I k d by 2 n minus 1 times sine of n k d by 2 divided by sine of k d by 2. If I take the mod square of g k, this comes out to be sine square n k d by 2 divided by sine square k d by 2. Now, let us do physical interpretation. From here, from each distance d, when the wave is traveling, and I am taking k in this direction, this is nothing but the original k and its component in this direction, which is nothing but k sin theta. So, this k that we are writing here is nothing but incoming k. Let me write for convenience k in sin theta. So, it is actually giving you the phase of the wave, and when I add over each source, right, so summation e raised to I k z delta z minus n d is nothing but sum of each amplitude. And what is this amplitude? Amplitude of wave from each source, and this is with the phase. So, I am actually adding the wave amplitude, and that is what I see. I see the interference because of this addition of wave. Now, important thing is that the amplitude of scattered wave is summation n e raised to I k z delta z minus n d, and this is equal to g k, and the intensity, which is equal to mod A square or proportional to mod A square, is proportional to sin square k d by 2 divided by times n sin square k d by 2. Which is nothing but g k square, and sin square n k d by 2 over sin square k d by 2 becomes large if k d by 2 equals n pi. How so? Because then you get 0 by 0, and I can then apply the L'Hopital rule to calculate this ratio. So, if I were to calculate the ratio of the amplitude, which was whatever e raised to something sin n k d by 2 over sin k d by 2 goes to n cosine of n k d by 2 divided by cosine of k d by 2, and at k d by 2 equals n pi, this becomes plus minus n. And for the rest of these values, it becomes very small. So, what you see, if you were to plot it with respect to k or k d, you will see that these becomes very large, 0, very large, 0, very large, 0, and these correspond to exactly k d by 2 equals n pi. And this is where the spots are. Let us see how so. So, k is this way, so what you are seeing is that there was a wave coming in, wave going out, this is k out, this is k in, this is 2 theta. So, this is where we see a bright spot. Then what you have because of this is, and this is k, that k by 2 equals k in or k out mod sine of theta. Now, k is such that k d by 2 equals n pi. So, this equation implies that n pi by 2 is equal to, k is nothing but 2 pi over lambda sin theta. K by 2 is n pi, so this is not going to be there, and this gives you right away n lambda equals 2, there was a d here, d sin theta. So, the interference condition is nothing but gives you the peaks at these Fourier transform sites. This function you can say the blue function is g k mod square. So, this gives us a way of looking at the diffraction pattern, and this tells you that think of the image plane as the Fourier space spanned by k vectors, and the Fourier transform of the scatterers gives the spots here on the image plane. So, whenever I have a diffraction and this diffraction or scattering is taking place due to certain scatterers, I take their Fourier transform, and whatever I see in that Fourier space is going to be the image that I see on the screen, and that is going to be our result in X-ray scattering also. So, what I wanted to show you through this simple example is that in optics, the familiar example of optics and diffraction grating, what you see in the image plane is actually a Fourier transform of these scatterers or the grating function. Now, we will take it to 3 dimensions. Now, one thing you notice here that the k or delta k, let me call this k same as delta k, is proportional to 1 over d. So, the image scale is 1 over d, where d is the spacing between the scatterers. So, similarly, when you see X-ray scattering through a crystal, the scale of scattering or scattered spots is going to be proportional to the inverse of the distance between the scatterers or the atoms in the lattice. Similarly, in Bragg's law, you think of these peaks coming from reflection through planes. So, delta k is going to be proportional to 1 over the distance between the planes, and that will connect it to Miller's indices also for the planes, because those are, remember, proportional to 1 over the distance. So, all these are connected. So, let us go to 3D. And we will specifically write scattering of X-rays from a crystal. Although we are doing it as scattering of X-rays from a crystal, this could equally well be applied to scattering of electrons from a crystal. So, let me ask you a question here. Which experiment established wave nature of electrons by diffracting them from a crystal? This could equally well apply to scattering of light from a collection of scatterers or a regular arrangement of scatterers. So, let us see now, I have an arrangement of atoms. Right now, I am considering no basis, simple lattice. In 3D, I am showing a 2D projection of it, and an X-ray comes in. And gets scattered. Another X-ray comes in and gets scattered, and they are all coherent. So, these are same X-ray. Now, let this distance be r. Let the projection of these here be this distance, and the projection out here be this distance. Let k in be the wave vector for the X-ray coming in, and let k out be the wave vector of the X-ray going out. So, if you look at only r, k in and k out, what you have is, here is r, here is k in, and here is k out. I can extend k in and make this angle like this. And I am interested in the phase difference between the wave coming here and a different point here. So, that phase difference would be these two distances added together. This whole thing has rotated by the k has deviated from the original path by 2 theta. Then the angles out here, this is going to be theta here and theta here. So, I can write the distance on the left hand side, the path difference, as r sin theta times k. Let us see if the angles are correct. The angle out here is this is r sin theta, and so is this r sin theta, or if this angle is slightly different, let us call it theta prime. Now, I think I am slightly off in the angle. So, let me just remake this figure. In the next slide, and what I am looking at is these scatterers. And the X-ray coming in, going out, X-ray coming in and going out. This distance is r. The angle from the surface is theta. So, if I draw a perpendicular here, this is going to be 90 minus theta, this is going to be theta, and this is k, this is r. So, between k and r, this angle is going to be pi by 2 minus theta. This is pi by 2 minus theta. Okay. So, what we have is these scatterers. This is r, ray coming in, ray going out, ray coming in, ray going out, and then I had drawn these perpendicular. This was r sin theta, and let us say this angle is theta prime, then this is r sin theta prime. And again making geometry clearly, this is r, this is k, and here is k prime, or k in and k out. I was writing k out and k in. So, if I add this path difference and this path difference, this is going to be k in mod r sin theta plus k out mod r sin theta prime. Since the angle out here is pi by 2 minus theta, I can write this as k in dot r, and the angle between k prime and r is greater than 90. So, I can write this as minus k out dot r. And therefore, the phase difference between X-rays from point at, say, let us say origin at and one at r is k in minus k out dot r. Now, I am going to add the X-rays coming from all these points. So, the net amplitude let us write it as a scalar A is going to be equal to summation e raised to I k in minus k out dot r I equals whatever all over 0 to n. I am adding over all these sides. And if I were to calculate the intensity, which is proportional to mod A square, it is going to be equal to summation I, summation j, e raised to I, let me call this delta k times R I minus R j. This could be minus dot it. What does it mean? Let us look at it from the atomic scatterer point of view. If there is an atom and there is a wave coming in, let us say e raised to I k in dot r, then the scattered wave or the total wave psi is given as e raised to I k n dot r plus a scattering factor f depending on the angle divided by r e raised to I k dot r. This is the original wave and the second term is the scattered wave. In our case, there are different atoms at different places. So, you are going to have the scattered wave as summation I f r, well, let us call it r prime and I will tell you what r prime is, divided by mod r prime e raised to I k dot r prime, where r prime is equal to r minus r I. Let us call it r prime I. Now, what you are doing is you are summing over all these waves, right. So, this becomes summation I f, let us say they are identical for each one of them. So, I will take it out, divided by r minus r I e raised to I k naught plus delta k dot r minus r I. I can take a certain quantities out, take them out as phase and you end up getting result same as this, except there is this factor 1 over r. So, I will just go very fast over it and tell you that the total amplitude then is going to be, assuming everything is identical, all the scattering strengths are identical, 1 over r e raised to I delta k dot r I minus r j summed over I and j, where I have taken mod r minus r I to be approximately equal to r in the denominator. So, mod A square, why do I keep writing vector here, I do not know, is proportional to 1 over r square summation e raised to I delta k dot r I minus r j. So, this gives intensity per unit solid angle in the direction k, which is equal to k in plus delta k. So, this intensity will be maximum if delta k dot r I minus r j is equal to two n pi. So, that e raised to I delta k dot r I minus r j is equal to 1 for all terms in the sum. So, condition, let us conclude on this condition for getting a bright spot in X-ray scattering is that delta k dot r I minus r j be equal to 2 n pi, where n is an integer, or delta k dot, this is nothing but a crystal vector. So, I can write this as sum n 1 a plus n 2 b plus n 3 c equals 2 n pi. So, your delta k, whenever it satisfies this condition, you are going to see a bright spot of scattered X-rays. Since we are assuming that there is an interference, is the same wave front of X-rays that is getting scattered from all the places. So, we have gotten the condition that delta k dot n 1 a plus n 2 b plus n 3 c is equal to 2 n pi for seeing a spot of diffracted X-ray. Now, this is done in 3D, except what is happening is, if you compare with what I did right at the beginning of the lecture, it is nothing but diffraction condition. You are making sure that there is constructive interference. And this condition can be written very simply as, or before that I should write A, B and C are unit vectors in the lattice. So, this can be written as long as I have delta k dot A equals sum 2 n 1 pi delta k dot B equals 2 n 2 pi and delta k dot C equals 2 n 3 pi. All three conditions satisfied give a bright spot of diffracted X-rays. These are known as Laue conditions. So, what it means is, if I have a vector A, that is vector A, lattice vector B and lattice vector C, condition that delta k dot A is 2 n 1 pi is nothing but the delta k lies on a cone this is delta k, such that this projection on A here is 2 n 1 pi. Similarly, for C, this fellow lies on a cone, so that there is a projection there, and for B also this fellow lies on a cone. And when all three conditions are satisfied, that means the three cones intersect along a line. When these three cones intersect along a line, we get a bright spot along that delta k. So, that is the way of looking at. So, in this crystal, all delta k's are there, but as long as these conditions are not satisfied, you are not going to get a diffraction spot. You get it when all three conditions are satisfied simultaneously. Now, taking advantage of this, now I am going to introduce something called the reciprocal lattice through this. So, introduction of reciprocal lattice. So, what we saw is that Laue conditions or Laue equations are delta k dot A equals 2 n 1 pi, delta k dot B equals 2 n 2 pi and delta k dot C equals 2 n 3 pi. So, this tells you that I can write in general delta k equals some n 1 a 1, where a 1 is a vector to be defined, plus n 2 b 1 plus n 3 c 1, such that a dot a 1 is equal to 2 pi, b dot b 1 is equal to 2 pi and c dot c 1 is equal to 2 pi. These are vectors which are very easy to define, and I am going to therefore write a 1 is equal to 2 pi b cross c over a dot b cross c. B 1 is equal to 2 pi c cross a divided by b dot c cross a, and c 1 equals 2 pi a cross b divided by C dot A cross B. So, these are well defined vectors, and to get a diffraction point, I should have delta k equals n 1 a 1 plus n 2 b 1 plus n 3 c 1. They are exactly like unit vectors, but in k space. So, these vectors give a lattice called reciprocal lattice. So, just like we have a lattice in regular space for the crystal, every crystal now has an associated reciprocal lattice. And the advantage of that reciprocal lattice is that any delta k, which is a vector in that lattice, is a possible direction of seeing an X-ray diffraction. Let us look at some reciprocal lattices. So, let me make for simple cubic I have the regular lattice. This is A, B, C, each with magnitude A in the x direction, y direction, and z direction. Then I have the reciprocal space vector A 1, which is equal to 2 pi B cross C over A dot B cross C. So, that gives you 2 pi A square in the direction of x divided by A cubed, which is 2 pi by A x. And similarly, you are going to get B 1, which is going to be 2 pi by A y, and C 1, which is going to be 2 pi by A z. So, you have the reciprocal lattice of simple cubic lattice is a simple cubic lattice with side of the cube equals 2 pi by A. Notice the dimension is 1 over L. This is precisely what we were noting earlier in the case of diffraction of light, that delta k was proportional to 1 over the distance. So, bigger the lattice in real space, smaller the unit or bigger the unit cell in regular lattice, smaller will be the unit cell in reciprocal lattice. Let us now look at BCC. In BCC, let me make the unit vectors first. I have 1 cube on the back side, 1 cube on the side, and 1 cube at the bottom. If I take this point here as O, then I know that A is here to the center, B is over here to the center, and C is over here to the center. This is from a lecture last week, and A is equal to A by 2 x plus y minus z. B is equal to A by 2 minus x plus y plus z, and C is equal to A by 2 x minus y plus z. These are the unit vectors, the primitive unit vector of BCC, and A dot B cross C, that is the volume of the unit cell, is A cubed by 2. Using these, I can calculate the reciprocal space vectors, and they come out to be A 1 equals 2 pi by A x plus y, B 1 is equal to 2 pi by A y plus z, and C 1 equals 2 pi by A z plus x. So, for this BCC, what I have in the reciprocal space is 3 unit vectors A, B, and C. These are the primitive vectors of FCC. So, reciprocal lattice of BCC is FCC. Similarly, you can show that for FCC lattice, the reciprocal lattice is BCC. I am going to give you a question now. Obtain the reciprocal lattice vectors for FCC and HCP. Brillouin lattices. Having introduced Laue condition for X-ray diffraction and reciprocal lattices, now let us go back to X-ray diffraction. So, we have seen that delta k should be equal to n 1 a 1 plus n 2 b 1 plus n 3 c 1. let us call this reciprocal space vector G, and what you see is that k prime or k out is going to be equal to k in plus G for diffraction. Until this happens, you are not going to get a spot, and still it is possible that you may not get all the spots that are given by this, but this is what it is. Now, in elastic X-ray scattering, that means the energy is not being lost, you are going to have k out magnitude equals k in magnitude. And this means k in square plus G square plus 2 k dot G is equal to k in square. This cancels, and you get a condition that 2 k dot G is equal to minus G square, or you can also write it plus G square by taking negative of G. Let us take the plus sign because that is more convenient. In that case, I am going to have k prime is equal to k minus G, or k out is equal to k in minus G for minus G. So, this is the other condition you get, that k dot G is going to be G square by 2 for elastic X-ray scattering. By elastic X-ray scattering means there is no loss of energy, therefore, the frequency and the wavelength of the scattered X-ray remains the same. So, we have got one more condition for X-ray scattering. Let us now geometrically interpret them. Let us write the conditions first. Conditions are now, one was Laue condition, which was that delta k dot A equals 2 n 1 pi delta k dot B equals 2 n 2 pi and delta k dot C equals 2 n 3 pi, and we interpret this as that the delta k being in a cone and the common line passing through all three cones give you the diffraction condition. The other one we got is that k out is going to be equal to k in plus G. And for this, we go to something called the Ewald construction. And what we do in this, let us make this reciprocal lattice. This is reciprocal lattice. And if there is a k coming in, then k out would be some sum of this k plus G. and for elastic X-ray scattering, this K in and K out has to be the same. So, that puts a very strict condition on which way the X-rays are going to go out once I know the incoming direction. So, I let this incoming K come in, add a G to it, so that K out is same in magnitude as K in, and this angle is going to be 2 theta. Third, I am going to introduce now something called the Brillouin zone. Now, imagine this reciprocal lattice, and I am going to make these points a little far. And I am taking a square lattice. And let me make the lattice vectors from one point to all the other points. I could take more, but this will suffice here. And let me now draw perpendicular bisectors of all these. Then the smallest cell that is made, the smallest cell which is out here, is going to be this. Let me make it even thicker. This is known as Brillouin zone. Notice that to any of this boundary, the wave vector or the vector is g by 2. So, if I look at this Brillouin zone, let me make it here now in thin font. This vector is g by 2. So, if I take any vector k to the Brillouin zone, k dot g by 2 is going to be equal to g by 2 square, or k dot g equals g square by 2, which is the diffraction condition. So, what we learn is that diffraction takes place when delta k is such that it is equal to g, and that gives you k out equals k in plus g, or equivalently when k out is from the center of the Brillouin zone to its boundary. That is a possible direction of X-ray diffraction. Why is that so? Let me make it slightly bigger in this same case. Here is the center of the Brillouin zone. Here is G by 2 and here is a K. This K can be written as K out here, which I will call K in plus G. So, it automatically satisfies the condition that K out is equal to K in plus G. I could add higher order of Brillouin zone and there also the condition would be satisfied. In the next lecture, I am going to show that the condition K dot G equals G square by 2 is equivalent to Bragg's condition for diffraction. So, with this, let me conclude this lecture. Fourier transform of a lattice gives the image lattice, which I am going to call reciprocal. Lattice, and this implies that delta K is a reciprocal lattice vector. Then we also obtained the condition that K dot G equals G square by 2 gives K for scattered X-rays such that a bright spot is observed. And finally, we are going to show that this is equivalent to the Bragg condition for X-ray diffraction. Thank you.